Our resource person, Dr. S. Jeba Berlin, Postdoctoral, IIIT Institute of Information Technology, Bangalore, who have graciously agreed to share her expertise and experiences with us. Your contributions will undoubtedly enrich our understanding and enhance our skills. I welcome you, ma'am. I also feel honored to welcome our respected correspondent and secretary, Very Reverend Father Satish Kumar, Bursar Reverend Father Hebin, and academic director, Professor Dr. N. Astin. To all the participants, I wish you a fruitful and engaging experience during this FDP. Let's make the most of this opportunity to learn, interact, and grow together. Once again, I welcome you all for this FDP and make this FDP a memorable and enriching experience for all. Now I invite Professor Dr. A. Lenin Fred, Principal, Marafram College of Engineering and Technology for the inaugural address.
Am I audible now?
Yes, sir. Yes, sir. Now.
Oh, now only. Oh, sorry. It was mute. Respected resource person, faculty members, research scholars, friends, good evening, what are present here. I'm very happy to deliver the inaugural address in this prestigious faculty development program. Two things. One is my own faculty members, they made the initiative for this faculty development program, organized a very grand manner. Another reason, the title of the faculty development program, next generation basics to the deep learning, discussing about and now Maraframe have made an initiative of thinking about next generation deep learning from the basics to the application. So I'm really happy about these two things. Friends, nowadays everywhere we were discussing about faculty development program. IIIT is initiated a lot of faculty development program in current areas. The central bodies, local bodies, the universities, colleges, and everywhere we can find faculty development program. Previously, some years before, you would like to join in a faculty development program, we have to wait for several months. But now you see, it's all in our fingertips. So, okay, next week is convenient for me. Just Google it. We can have some list of faculty development program in our convenient days. We can select one among that. So, a lot of awareness in the faculty. So, okay, next have some specific reason. Just why Google it. Lot of awareness. We can have in faculty development program, friends, updating ourselves with the current changes in our relevant field. We are all engineers, especially computer science and engineering field. in our field, what all the current changes happen, we should have an awareness. We should know more about that. That's why the faculty development program is very, very important, and everybody is encouraging and initiating a lot of faculty development programs. Friends, you consider a knife or a tool. In some specific intervals, we should sharpen that knife. Otherwise, it may be a useless one. We can't able to effectively, we can't able to use that knife. The knife may be very sharp, maybe 1 month before. It's very sharp. But after 6 months, if you are not sharpening the knife, you can't able to utilize the knife for the purpose. The same way, as a faculty, you may be an effective, very effective faculty now, but you are not updating yourself with the current changes in your relevant field. I'm sorry, after 6 months, or after 1 year, or after 10 years, you may not be a useful person in our teaching field. That's why please join wholeheartedly with this faculty development program. Listen the resource persons' lectures, interact with them, and you can get the contact details of them. In future also, in your research, in your publications, if you want more clarification on that, you can contact the resource persons. There is the right opportunity for you all. My dear friends, we are all in the teaching field. Majority of, I hope so, majority of the participants are in the teaching field or aspiring teachers. Friends, knowledge is the power of the teacher. The teacher is more knowledgeable, more skillful. That is the real power of the teacher. So, if you are having the current technology, if you are aware about the current changes, definitely you will relate all these changes in your lectures. All your content delivery, you will connect all the current technology with the syllabus. Then the students always having the curiosity to listen your lectures, because they don't want syllabus now. That syllabus content, they will read it from the textbooks. The effective teacher means always linking the syllabus content with the current technologies. That is the need of the hour. Automatically, you will get more respect from your students. And another very important thing, what I mentioned here is lifelong learning. Friends, don't stop learning in any part of your life. Nowadays, you may be an expert in deep learning. Don't stop. Go on, go on. So always, that is called as lifelong learning. Till our end of our career, we should update ourselves. Otherwise, we are no more in our field. No more in our field. Lifelong learning is not like degrees. I'm not mentioning about the degrees. Yeah, always degrees are more important. But other than the degrees, like this faculty development program, update your knowledge and skills. That I'm telling about lifelong learning. Then you are more powerful, more powerful teacher. In this way, I really appreciate the organizing team, especially Professor Dr. Herlin, Janila, and other team members for organizing a wonderful faculty development program in a current that is emerging area. And also I appreciate all the resource persons who have accepted to deliver and share their technology, their knowledge and skill. I'm really happy. I really appreciate all the resource persons. And also I appreciate all the participants. So now in my screen, it's showing that 77 participants. Now it makes 78. So really happy. How many participants are that is very much interested to listen this FDP. Really, I'm very happy to give an inauguratus and inaugurate this faculty development program. So listen the faculty, all the resource persons talk, interact with them, get connect with them, and do wonderful research in your career. So once again, I appreciate all of you. Thank you so much. Thank you for the opportunity given to me. Thank you.
Thank you, sir. Now I call upon Ms. Janila, Assistant Professor, Department of Computer Science and Engineering, to address the today's resource person.
Thank you, Dr. Herlin, ma'am. It gives me immense pleasure to introduce our resource person, Dr. S. Jeba Berlin. Dr. S. Jeba Berlin holds a Bachelor of Engineering and a Master of Engineering degree in Electronics and Communication Engineering from Anna University. She subsequently received her PhD degree in Information and Communication Engineering from Anna University, focusing on human action recognition and data learning models. She is currently a postdoctoral researcher in the Multimodal Perception Lab at IIIT, Bangalore. Her current project, in collaboration with St. John's Hospital, Bangalore, aims to enable earlier diagnosis of autism by analyzing children's play behaviors. I feel she is the opt person to give an introduction about the deep learning concepts for today's FTP. And with immense pleasure, I welcome you, ma'am, and we are eagerly looking forward for your session. Ma'am.
Thank you so much for the nice introduction. So it's been a pleasure to be a part of this FDP. Can you hear? Is it audible?
Yes, ma'am. Yes.
So, shall I start? Or is there?
Okay, ma'am.
Okay, thank you. Can I see my screen? Can I see my screen?
Yes, ma'am. Yes.
Yeah. So thank you so much. So just talking, so I just want to talk about recent trends in deep learning. So as Miss Janila given the introduction about me, I'm like postdoctoral researchers working in multimodal perception lab in IIIT Bangalore. So this is the roadmap of today's presentation. So first, since today, this is the first day of FDP, so I just tried to brainstorm a little bit about the machine learning basics. So I will start up with machine learning basics and basics of deep learning. Then what are the components used in deep learning? Then different types of learning that has been used in the machine learning application. Then different applications of deep learning, then explainability models, generative models, then the recent deep learning architecture that has been used everywhere, which is the transformer architecture. And finally, I will give little bit about the agentic AI. So coming to the first part, like it's the machine machine learning basics. So actually, using the machine learning, we can perform two tasks, mainly two tasks, that is the classification task and the regression task. So the classification is nothing but like so which class the given input is. So just to classify which which category the given input is, and the prediction and the regression in the sense to predict something from the input. Like given the input, we are going to predict something using the information from the input. So this is like linear. We have, for example, so this is the basic architecture of linear regression. We have, so since I'm working with image and video, so I think most of my present slides I have image and the video as the input. So here when we consider this as the input, so we know that input to the image is like the pixel. So the pixel is the input to the linear regression. So since it is a logistic regression model, we have the sigmoid function. So this is actually the classifier is nothing but like, so we have a model. So we are trying to learn some features from the input image. So through training, and during inference, when we give some inputs, so whatever features the the model has been trained so far, using that features, it will give a plant as well as the dog. So here you see, like even the dog predicted probability is 0.8 and predicted probability is 0.7. Whereas here you see like, so it's 0.5, it's 0.4. So any one of this thing is dominant. Like, so here, so we can basically use like in the output class, we can either use sigmoid or softmax. This is the like, so output layer, we have either sigmoid or softmax function. So when you use the sigmoid is that like if you need more than one label, like say in the multi-label classification problem, mainly the last so the output layer will have the sigmoid activation function. Whereas if you have multi-class classification problem, we will use the softmax output. This output is, this activation function is sigmoid for multi-label classification problem, and it is softmax for multi-class classification problem. And these labels, maybe we can have these labels either as the one-hot encoding or as the numerical labels. One-hot encoding in the sense, for example, if you have 4 labels, we can say like for the first label, the first position will have 1, and for the second label, the second position takes value 1. Similarly, like so for the third label, the third position takes 1. So also we can train the model using numerical labels. For example, say if you have 4 like classes, we can label it as 0, 1, 2, and 3. So that's based on our so our convenience, we can label the things. So this is the basic machine learning architecture. This is the neural network architecture. So coming when we jump to the machine learning to neural network architecture, we have like input layer, hidden layer, then activation. So then move on to the convolutional neural network, we have more number of hidden layers. So the difference between the neural network and the convolution and the deep neural network is like we have more hidden layers in like deep learning architecture. So what is the purpose of like introducing more hidden layers in the sense, if it is a simple classification problem, it is enough to like extract few features from the input. Whereas if you go for a more complex task, for example, we say in this images we have the face of different different people. So here we have here the features are, we have eyes, nose, like mouth. So for each and every person, those things will vary. So in order to capture those things, we have to have more number of hidden layers. For example, So as you can see from this diagram, the hidden layer 1 is responsible for capturing the edges. So here in this diagram, we have 3 hidden layers. The first one is responsible for capturing the edges. So it will capture different types of edges. Say like diagonal edges, then vertical edges, then horizontal edges, then left to right diagonal. So different type, it captures different types of edges. Whereas the hidden layer 2 is like responsible for capturing different components present in the faces. For example, say nose, eyes. So here you can see it captures the eyes, nose, then like ears, those things. Similarly, the hidden layer 3 is responsible for capturing the face, the entire face. So each and every, so as the number of, as the depth of the network increases, so it captures more complex features.
Excuse me, ma'am, 1 minute. Dear participants, please mute your devices. Dear participants, please mute your devices. Jeba ma'am, can you mute your device?
Yeah, sure.
Not Jeba ma'am, Jeba ma'am. Jeba ma'am, you can continue.
Sorry. Good.
Jelba ma'am, kindly mute your mic, ma'am. Jelba ma'am, can you hear me?
One OB இன்னொரு புக் உண்டுல அதை எடு இங்கிலீஷ்ல. நான் உனக்கு என்னல சொன்னேன் இப்படி நீக்கி எழுதாதல்ல அந்த
Ma'am, you can continue.
Yeah, thank you so much. Like so, earlier layers are responsible for capturing the simple features like edges, whereas the middle layer is responsible for capturing like some specific patterns from the input images. Whereas as the depth increases, it is responsible for capturing more complex features. So this is like so when we are so try to deploy some deep learning project, these are the things we should consider of. First, collection of data and the preparation of data. The preparation of the data includes like some post-processing procedures, some augmentation procedures. Then design, we should have an idea like what architecture can be used for the particular application. Then the training the model, then the inferencing. So these are the basic things or hyperparameters or components which we can see in any deep learning architecture or maybe in machine learning or something. Like first thing we should take care of is like weight initialization. So in the earlier networks, actually they start initializing the neural network with zeros or ones. So now there are various methods for weight initialization, like the Savier's method, there are different Hutch initialization, different types of initialization. So when coming to deep learning architecture, even the initialization of weights plays a vital role in converging in the convergence of the network. And the next thing is loss function. So loss function, it decides like, for example, if you are using, if you have regression problem, then we will compute L1 means L1's like L1, L2 mean square error, L1 square error, so mean square error, so those things. Whereas coming to the classification problem, we will use the cross entropy. Then for binary classification, we use binary cross entropy loss. So we should fix the loss function properly. So only then the network will be able to learn the features in a better way. Then the next parameter we should take into account is learning rate. So here it's a hyperparameter. So if we choose, suppose if the learning rate is too low, it takes in order, consider this is the maximum point we have to attain. So this is the cost function and this is the weight. So this is the global minimum we should go. So if we choose the very small learning rate, it takes more time to attain this global minimum value. So similarly, if it is like too large, the model won't even converge. It diverges here and there, and it won't even go to that global maximum. So that just it's like the optimum way of choosing the learning parameter is like, first we start with the highest learning rate, then after few iteration we have to reduce the learning rate, then after few iteration we have to further reduce the learning rate. So as we approach the global minimum, we should reduce the learning rate further and further. So this reducing the learning rate can be done using the schedulers. So the scheduler plays a vital role in varying the learning rate at different epochs. Then optimizers. So there are different types of optimizers. We can't say like this optimizer is best or this is best, because for every applications, the optimizer the different optimizer will give the different result. So these are the different actually what is the purpose of optimizer is like, what the machine learning architecture will do, like, so this is the output layer. We will pass the gradient from here to the input. So while passing the gradient, so based on the difference in the predicted and the true label, so it will generate some gradient value. So based on that particular gradient, these weights get updated. So here, this optimizer will decide in what direction it has to go. Like, so it has to go downward, like it was to, this is the 3D, in the 3D structure, it's like, so whether it has to go down or go up, or what direction it has to take. Then the activation functions. Basically, the activation function is nothing but in the deep learning, so the architecture is it's so deep. So when we start from the input to the output, so it's like it's a sequence of products like multiplication and summation. So when we do like multiplication of summation, the product of summation, so we will end up with some huge value. So if we have that so much huge value, the computation of gradient is somehow difficult, and the model won't like respond in a right way. So we will have every node will have an activation function. This is like to, it's just like, for example, if you say like sigmoid activation function, if you use sigmoid activation function, like whatever value is there, so it map everything between 0 and 1. Similarly, relu, gelu. So there are a lot of activation function. Basically, what it does is like, so whatever may be the input, it like makes the output to some desired range, so that the model cannot diverge like due to this huge value. So this is the normalization. So now basically the normalization can be done for the inputs. The input is like, so when we normalize the data, we will get the like uh, input with mean 0 and std 1, so that even this helps the model to like helps in better convergence, as well as like reduce underfitting, so those things and all. So basically whatever may be the input, it is better to do like normalization. It may be min-max normalization or standard normalization, whatever may be, it's the better choice to start with the normalization of inputs. And this is the next like there are different types of learning. So basically there are three types of learning: supervised, unsupervised, and the reinforcement learning. So we all know supervised learning in the sense we know the input and its label. So we train the model saying like, this is the input, okay, this is the input and this is the label. So you train you learn something from this input if the label is this thing. So we will provide the model both the input as well as the label. Whereas in the unsupervised learning, we will provide only the inputs, and based on some similarity score or some distance, it will group the input in different clusters. Say, so the apple. So if we give different fruits, it will clusters into different groups. And similarly, this is also a type of supervised learning. So for example, here this is the input data. We have two dogs. So this is like object detection. So it detects, it localizes the object present in the input. So this is also a supervised learning. So we know where it, so we train the model saying this is the position of these objects. And when we give the input data, so it will another new unseen data, it will label the particular objects from the given input. Similarly, this is like here the output is skeletal joints. So this model has been trained with skeletal joints. Similarly, this is like reinforcement learning. Reinforcement learning in the sense, so we have no labels, like so here we are giving the reward. For example, so the model trains by itself, like we don't provide any labels or something else. So for example, if the if for example, if this toy has to go right, and whether it takes, if it takes the right direction, so we will give some reward as plus 100. Whereas if it takes the wrong direction, we will give some punishment. Here the punishment in the sense, we will give the negative rewards to the model, so that with the help of the reward given to it, it either it understand like so if the reward is positive, it understand that we took the right move. Whereas if the reward is minus, it understand itself like, oh, we took the wrong move. So it learns itself based on the reward given to it. So then the next thing is like zero shot learning. Zero shot learning is nothing but, so here the data set has been trained with some data set. The model has been trained with some data set, and so for example, you say like, so we have a bird data set. So in the bird data set, what we are trained with is like, so if the the particular bird has tail or fur or feathers, whiskers, beak. So this model has been trained only with the bird to to determine whether these features are present or not. So during inference, we are giving it's different from bird. We are giving a new data set which has only dog. So if we give dog as the input, it gives tail. So if it's tail, if it has tail, it gives us 1. Fire, if it has fire, it 1. Then further 0. So it has been trained with some data set and inference has been done with some other data set. So that is zero shot learning. So the so this is the pre-task and this is the downstream task. So both are we are performing with the different data sets. And this is the transfer learning. The transfer learning is nothing but so when coming to the deep learning architectures, the one main drawback is we should, it's like data data starving architecture. It needs more data to train. So for example, if we have some medical application, so we don't have, so we should not have that much huge data set. So what we will do is we take some pre-trained model which has been trained with millions of inputs, and so this is the pre-trained model which has been trained with some publicly available data set which has more number of input samples. And so for example, if we want to do classification so if our task is about so some medical input, say so from the MRI image, if you want to predict some disease, so what we will do is we will use the same base as the pre-trained architecture, which so this is transfer learning in the sense, so these weights are fixed. Whatever weights has been trained with this data set, we will frozen those weights, and we will remove only these 2 layers and replace it with the new layers, and we will update only these weights. So the first few layers were frozen, and only the last few layers we will train train only the last few layers. So that is called transfer learning. We are transferring the knowledge that has been obtained through this data set, is that has been used by our new data set. So that is transfer learning. So also you may hear about the self-supervised learning. So when to is the self-supervised learning is say for example, so if we have only small data set, but this small data set is not so we need so in order to train the deep learning model, this small data set is not enough. We need more data to train those models. So in that case, what we would do is from the from our data, so what we will do is this is for example, if our input has image data, so we will say we will black out few portion of the input image, and we ask the model to find this missing portion. Similarly, if we have some for example, if we have video input, what we will say is for example, so our task is to find say we have a video which has some cars or some bike and some buses. So what we would like to so what we during the pre-task, what we will say is we have to ordering the frames. So we will do frame ordering during this pre-task. So that doesn't need any label. So we just shuffle the order of the videos, and we just we make the model to learn the order of the particular video. So that is the pre-test task. And this target task is like, so we want to like find out what like particular video has. The same thing is for video. For example, if you have this as the CAD, so we will just black out few portions of the image, and during the pre-test task, what we will do is we ask the model to find out these missing patches. Similarly for this, like so we want to learn the model to find out the missing patches, whereas in the target task we will give this cat image as the input and ask the model to predict its label. So this is like this scenario, the self-supervised learning, which we can use this type of learning when we have like fewer like smaller data sets. Similarly, active learning in the sense, if we have large data set and if it's difficult to label the entire data set, what we will do is like we will pick, for example, if we have billion data set, so we will pick only 50,000 images from the data set. We human annotators, we label those data, we train the model with that data. And so whatever data is uncertain, for example, if for some for some inputs we have the prediction probability ranges from 0.4 to 0.6. So here it's like we can't say like the prediction is more high. It's like it's in the borderline. So we will pick only those inputs and we will manually annotate those data set, and then we include that data set to the first annotated data set, and we retrain the model. So first human annotator, so we pick some samples, then we annotate, then give it to the model, then it will give the prediction. Then so we will pick some like uncertain predictions, the images which have some uncertain prediction, then we will annotate it, then given to the model. So the process goes on. So it's not necessary to label. So the human workforce is not required to label all the data set, whereas so we will annotate only if the particular label is uncertain. So these are the different types of learning. Basically, active learning, zero-shot learning, self-supervised transfer learning, these are the things, learning which has been basically used in the deep learning architectures. So then let's talk about so deep learning in healthcare. So similarly, so in most of the healthcare applications, so now they are using the deep learning like cancer detection. Then from the MRI image or from CT image, they can MRI image or from CT image, they can detect what disease the particular person is having, or localize we can do the fetal localization, or some blood samples we can diagnose what the particular person is having. Like so in most of the medical so most of the medical imaging has been so the deep learning has been used in most of the medical applications. For example, this is like one of the projects that has been done by the Stanford. So here we can upload our X-ray, like we can upload the X-ray of us, and it can say what disease we have. Like so it displays the probability of the particular disease. So this is this is the heat map. Heat map is nothing but, for example, so in this diagram we can see this is the area where the tumor is. So for example, so here this is the bright area. So this signifies like So this region corresponds the model, is responsible for the model to give this prediction. So if this part is somewhat bulge, then we can say like this cardio something, the disease, this particular disease is present to that particular patient. So this is like some we call this as explainability, like saliency map. So which makes the model to give this prediction. So here we can see this portion makes the model to give this prediction. Similarly, this is like for fracture detection. So if we give the feed the uh, X-ray to X-ray to the deep learning model, so it can say like it can spot where the fracture is. So this is the place where the fracture is. So this is one of the application where deep learning has been used. So this is actually the explainability from an image. Actually, this doesn't belongs to deep learning. This explainability, basically, this is the sharp explanation as well as the lime explanation. This is for 1D. So for example, if we have 1D input, say we have the attributes as age, hypertension, sex, then sodium, UPROs. These are some attributes we have from particular patient. And so this is like if the particular patient is having the cardiac disease or not. So for example, so here using the sharp, we can say like the feature importance. Here we can say the age is the main factor. Like the age is the factor that influence the model to this prediction. Then followed by hypertension, then followed by sex. Where HDL has the very low importance. So when we see this diagram, so this is like so when we plot the whole like data sample from the data set, we see like, so this is the sharp value, we have the highest value, this is the negative sharp values. So the highest sharp value says like these features are like positively influence to the model prediction. For example, age, hypertension, and sex. Sodium is little bit like so these are like so if this increases, model prediction will also increases. Whereas antiplatelet drugs, GGFR, this has the negative impact on like cardiovascular disease. So this has a positive impact, this has the negative impact. Similarly, the lime explanation. So basic, this is all this, with this also we can say like which the importance of features in the particular data set. So these are the positively influential features. The green ones are the positive influential features, and these are the negatively influential features. So if AKS is high, so there is the patient like is severe with some disease, like say similarly AST, the next highly influential feature. So likewise, we can find out the importance of different features that has been obtained from the patient. So earlier, actually, the neural networks were thought as the like black box. We don't know what is happening inside the neural networks. But now we have more explainability models, so that we can so interpretable model, interpretability, explainability, so that we can like it helps us to understand which makes the model prediction in this way. This is like since I'm working with autism child, this is just a video clip that so
then we're able to
basically what this robot does, like it, so it has a video sensor and image sensor. It captures the facial expression of the child and what the child is doing. So in the imitation task and all, the robot will ask the child to do something, and the child will follow that whatever the robot is doing. Basically the autism child, like they the social, they have poor social communication. So they feel bit difficult to interact with the humans, and they interact more with the so objects rather than the human. So the research study says, like with the intervention with an robots will will have a more progress with the autism child rather than with the human being. So this is so also the deep learning architectures that has been used in the rehabilitation, for the rehabilitation purposes as well. So here what the thing is, so here uh, so it's very difficult, maybe whatever maybe the physical rehabilitation or physiotherapy is very difficult to get appointment with the clinicians. So we have to so we have to wait for a long period, or so that what they will do is they suggest us to do something from the home. So in order to the clinicians should have the feedback from us. So in order to get feedback from us, so they're asking the patients to do some the required exercise or required moves from the home itself, and they want to record the particular things, and it has been sent to the clinician, and they will they will provide a feedback to the patients. For example, this is like exercise, so they will provide some exercise as a physiotherapy, so here they have the post estimation. These are the skeletal joints that has been generated using some deep learning architectures. And if there are some so if for every poses, the skeletal joints should be in the particular position. For example, here this is somehow deviated. So if the particular thing is deviated, in some cases it will be shown immediately in the screen, so please move this joint little bit up or down. So it provides a feedback lively, or maybe so we can record these things and we can send to them, and there will be model in their centers, and they will provide feedback later. So either the feedback can be it can be given lively or little bit delay. So similarly here, so for example, if the person has done some joint surgery, or some they have some injury, so they have to so it's very so the patients are asked to do move the limbs from their homes. So here they will just day to day, how the joint angle varies day to day. For example, during the surgery, after 1 or 2 days of surgery, the patient cannot move their limbs. So after day by day they can move. So at what angle the particular movement has been taken, so whether it attains the so here only the angle difference is considered. So for example, only the limb movement, so only the angle variation has been considered. The next interesting thing, like in the deep learning, is like generative models. So we can now everywhere we can we can see more synthesized images, synthesized generated videos everywhere. So basically, there are two models, two generative models. One is the generative models, as well as the diffusion models. So this is the diffusion model. So here during the forward propagation, like diffusion, we will add some noise to the image, and we will make the model to reconstruct some image, give like from this noisy data. So this is how the diffusion model works. So, and this is the generative, how this GAN works is like, so we have the training data set. Here we will start from some noise image. So we have both generated and discriminator. So from this noise image, this generator will generate some image, and the image from the data set and this generated image has been compared using some discriminator, and the learning goes on until it converges. So this is how the generative model works. So actually this is like, this is an image generated through the diffusion model. So to say, if we prompt the model with a golden retriever dog wearing a black, like blue checked beret and red dotted turtleneck. So first it will, the text to image diffusion model will generate this image. So if we want to increase the resolution of the image, we will pass it to super resolution diffusion model. If you want to further increase the resolution model, we have to further send it to this model. So this is how using this prompt, this image has been generated. So these are the different images that has been generated using a prompt. Say this is the text to image. So some prompt has been given and this image has been generated. Say it's like only say omnigen quality. So this is like, this is also a prompt. So this, in this, what in the prompt they have mentioned how this lady looks like. So how the hair would be, how the eyebrows would be. So whatever the details has been given in the prompt, and according to that, this image has been generated. Similarly, these things. So here reasoning, in the reasoning thing, what the thing is like, where can I wash my hands? So if we ask, if we given this image and given this prompt, where can I wash my hands? Please help me find the right place. So so this model locate the particular place. So this is the basin. So it locates the particular place where we can wash the hands. Similarly, here some portion has been removed. This cup has been removed. So here from these two images, a new image has been generated with a given prompt. Similarly, this is also a new image has been generated. So here depth image is given, and from the depth image, a new image has been generated. Similarly, from here, some other image has been generated. So when we ask this, given this image, if we ask the model to deblur this image, so it will deblur the image. Similarly, we can ask the model to generate the skeletal joints. So if we paint the particular portion, it will fill up. So the color of the hair or some part of the things can be changed. So whatever is given in the so given in the prompt, so the particular deep learning model will perform the particular task. So this is like the step-by-step generation of the particular images. So basically these are the generated images using different prompts. And this is like image to image translation. So if we have the label, semantic label of an image, we can generate a new image. Similarly, if you want to generate this building, so just given as some blocks, say horizontal, vertical blocks placed in some alignment, so we can able to generate this image. Then black and white to color, input to like aerial to map, day to night. If you give edge of the particular, so what is like, so for all these examples, like there should be like some dedicated model. So with this, for this labels to street scene, there is some specific model. For labels to facet, there is another model. For this, there is another model. So for each and every case, like edge to photo, in the sense we have a specific model for edge to photo. So specific model for like every image to, like for every images. And this is like generated videos using prompt. So these are also using diffusion. They have used diffusion models, given the prompt saying the camera directly faces colorful buildings in Verona, Italy. So this is like, so they prompt a model with this thing and it generates this image. Similarly, when they prompt a stylish woman walks down a street in Tokyo filled with warm glowing neon. So this is also a generated image for this prompt. So these are the images generated using the diffusion models. So see how realistic it like the video is like. So since I'm working on like human to object interaction, so just I want to give a glimpse about these things. Like so this is like, so we can this is here the child is playing or some with some partner or with some expert like examiner or clinician or caregiver. So here we can through this like through the gaze following model, what we can observe is like where the particular person is looking on or gazing on. So for example, here this particular person is looking on this toy and also this child is also looking on this toy. Whereas here they are looking face to face. There is some eye contact. So we can so we can like find like where the particular person is facing to. So that can be determined using some gaze following architectures. Similarly, human to object interaction. So here a lady is carrying a bag, then tennis bat, and also he's like has a dog. Like so here we have more interactions. That the lady is having this bat, holding tennis racket. Similarly, has a bag. Similarly, has a dog. So this is like multi-label classification. Within a single image, we have more labels. So walking dog. So first, what it will do is it will detect all the objects. This person, these are the objects, and how the lady is interacting with a particular object. So here the walking dog, the probability is 0.69, holding tennis. So for each and every interaction, what is the probability? So it will this model displays those things as well. Similarly, this is like tracking. So here we can try if we have multiple persons in the scene. So we can give some ID to the person and we can track the particular person. So similarly, this is like pose generation. So this poses we have already seen in previous slides. So there are architectures to determine the pose as well. Also action detection. So here it's like spatio-temporal action detection. The spatio-temporal in the sense we can predict both the location, spatial location of the particular person as well as what are the particular so time frame as well, both the spatial location as well as the temporal location of each and every person and what the particular person is doing. So here like this person is watching to other talk to person, carry object, stand. So each person, this is also a multi-label problem. So there are more number of labels for a person. So this is a multi-label problem. So these are like there are few architectures to like compute the facial landmarks. So this is one of the autism kit where we are extracting the facial features and how where the eye points to how the gaze of the particular child, where the gaze points towards. Like similarly, this is like how the key point is generated for the particular kid. So then coming to the next, so, so after so the like deep learning architecture, the transformers has been taking over most of the deep learning architectures, because for the last few years, transformers is performing better than the most of the deep learning architectures. And in most of the natural large languages models, so wherever they are using transformers, say ChatGPT or some other agentic AI, wherever we can see transformers everywhere. So let me touch little bit about the transformers as well. So this is the transformers in computer vision task. So here basically, so transformers, first it has been used in the language NLP, then now it has been used for every task, computer vision or some other task. Everywhere the transformers is so they are using everywhere. So this is how the transformer architecture looks like. It has the encoder as well as the decoder. So in the NLP, what is the function of this transformer is like, for example, input is say, how are you? So here it takes, we give how are you to this input, and I'm fine as the output. So here if we given how are you, the input embedding, so how are you, so for each word it generates some input embedding, then some positional embedding. So says like how should be, R should be followed by how, and you should be followed by R. So there should be positional encoding to understand the position of the particular words. For input embedding, there are multiple architectures so to generate the embedding from the given word. So here, this encoder is responsible for capturing some context-related encoding, and this has been fed to the decoder. So what the decoder will do is, it takes the input from this encoder as well as from the, this is like, for example, if it wanted model the train, want the model to train how are you as the output, and I am fine as the I am fine as the output, and how are you as the input. So this output is I am fine. So the same process. So it encodes I am fine, then add positional embedding, then do multiple attention, then it has been merged with the encoder output, then do some process multi-head attention, then it will find out some probability. So actually this transformer model has been used for machine translation to predict the next word in the sequence. So whatever may be, so we can do with the transformer architectures. So in computer vision, what it will do is like, here the patches is nothing but, so here we have how are you, we have 3 words, so we have 3 word embeddings. So here in this input image we have 9 patches. So each patch is is a single is a single embedding. So we have different patches. If it is a time sequence data, this takes first time sequence data, second time sequence, so third. So whatever may be, it may be a word, or it may be an image, it may be some time sequence, whatever may be. So this is the input. Then there will be some project. This is the linear layer. Then this is the so basically, if you want to perform some classification task, it is enough to use the encoder part. This decoder part is to generate something. So here our task is to do only the classification. So it's enough to have the transformer encoder. So after the transformer encoder is followed by some classifier head. So these are the class labels we have. Also, we have some saliency map. So score cam. This is just like to locate where the particular thing is. So this bacteria, something like to locate these object. So we have saliency map. So with this, both the classification and the this is this is a sort of explainability in 2D image, like to explain what make this model to predict this as this particular category. This is given this image, So this architecture is able to like generate some text from this image. Say this is if this is the input, and this model generates a little girl holding a kitten next to a blue fence. So it's like basically like image captioning something. And the next thing is like, so transformers in NLP is like, this is basically a chat GPT architecture. So I'm like, so we are all aware of chat GPT now. So actually there are two types of learning takes place in the chat GPT. One is the supervised part, otherwise is the reinforced part. So first we will pick some input samples and we will try to do supervised, like this is the fine tune architecture. So we will do supervised learning first. So step one, we will do supervised learning, and in the step two, we give new prompt and like give some response, get some response from this model. And here there is some human, we need some human like annotator to gen- to generate the rewards for the answers. For example, like say, so where is Mara from? For example, let's say where is Mara from? So it's located in so Kanyakumari, or it is located in Martandam. It's located in, so the different answers will be generated using the using the same prompt, and the human annotators will label the that answer. And so there is one more separate architecture, that is the reward model. So there is a cell, this is like, this is the basic model, this is the reward model. So basically this reward model trains this SFT model based on the rewards given by this human annotator. So this the updation of this reward model continues until like the model converges, or until we attain some desired results. So when we so during inference, when we give new, so we will take this, we will give inference to this STF model. For example, here you see, like, so during inference we give write a story about otters. This is to like this model, STF model, and it will generate some reward, like say. So then the last thing is like, so here nowadays everyone is buzzing about the agentic AI. So wherever we can see, so wherever, so most of the areas, in most of the areas they are using the agentic AI. So it has been used in various applications like game playing, then robotics, autonomous vehicle, then like chatbots, then we have virtual health assistants. Even in education, we can provide personalized education for kids, then even trading recommendation systems, scientific discovery, that is a protein structure that has been we can study the protein structures, everything. So everywhere we can see the agentic AI. So finally, like, let me conclude my talk. So by displaying this videos, maybe our future may looks like this. Like, this is the human agentic AI that has been generated using some simulators. So some prompt has been given to the particular agent, and it is performing some specific task. So if we give the prompt to set up a workplace, so it is first it detects the objects. So it detects the monitor, then organize the shoes. So it detects where the shoe is and keep it in its desired place. Do laundry. If we do ask the agent to do the laundry, it detects the laundry basket and do the stuff. Similarly, like so if we prompt the agent as clean the living room so that I can play yoga in front of the TV. So it identifies where the TV is, it detects then what are the objects in front of the TV, and it just dislocate the things. Who knows, maybe our feature may also looks like this. So with more agents like doing. So thank you so much. That's the end of my presentation. I hope it's somehow useful for you. Any queries?
Any queries from the participant side?
So I think no queries, Herlin ma'am. So shall we conclude?
Yeah, sure, ma'am. So
So
thank you so much for once again. Thank you so much for giving me this opportunity. Like,
thank you, Dr. Jeba Berlin, ma'am. Thank you for sharing your knowledge with us, and thank you for spending your valuable time with us, ma'am. It was really very informative session. We gained a thorough knowledge about the introduction of deep learning and its applications. Thank you so much, ma'am. Thank you for sharing with us.
thank you so much.
Thank you, ma'am. Thank you, participants. Feedback link is posted in the YouTube and also in the chat box.
Ma'am, it is not opening.
Okay, I'll check it.
Jeba ma'am, we have a query here. What is augmentation?
Yeah.
From Mary Aida.
Yeah, actually, the augmentation is nothing but for example, you see, so when we consider the image input, uh, uh, if you train the model only with a particular images, so there is a possibility of overfitting the model. So it learns so if we give new inputs, it's not able to generalize. Like for example, if you give exact dog to the model for training, so what we will do is we will add some noise to the input, or we may crop some portion of the training data set. We don't know how the test input image looks like. So there may be some occluded region, so or there may be some noise in the input image. So while training, we add some noise or we crop some portion. So those things, like whatever possibility, so we predict, so guessing that these are the noises that can be present in the input image, like inference image, and we train the model accordingly, like with noise or some with croppings, those things. So that can be called as the augmentation.
Thank you, ma'am. We have another one query from Sylvia, ma'am, it seems. She raised her hand. Sylvia, ma'am, please proceed. Okay, no response yet from her side. We have another one query as well, ma'am. Can you suggest suitable transformer model for disease prediction?
Actually, we can't say so this is the model suitable for this. We have disease, in the sense we have the input may be in the form of EEG, or maybe CT or MRI, or some tabular data. So based on what the input, so we can use different transformer model. For example, we say if we have image input, we can use VIT transformers. For if we have some video input, we are having that transformers that can accept video as the input, swing transformers. There are a lot of transformers. So whatever is best suited for you, the particular disease, we can pick that model and we can use that one.
Thank you, ma'am. We have another one query. How to incorporate novelty in a pre-existing deep learning model?
Novelty in the pre-existing deep learning model. So this thing that is we can't say like this. The novelty, it varies, right? So maybe we can include some attention mechanisms in the model, or maybe we can have some different activation functions, or we can introduce new learning algorithms, say we can have active learning, self-supervised learning. So we can introduce new learning algorithms. So it's not like in one it's a broader thing, so we can't say in this a component we can have a novelty. It's in there are multiple components in the deep learning architectures. We can have novelty in any of the components as of our interest.
Okay, ma'am. Thank you. Thank you so much for sharing your valuable time, ma'am. Thank you so much.
Thank you so
Herlin,
much.
ma'am, shall we wind up?
Ma'am, the feedback link is asking access. I think it's not open now yet. Can you please release it?
Okay, sir. We'll check it. Okay, ma'am. Please wind up.
Fast